Hello class, this is a video tutorial on the volume of solids. Let's consider the area of the simple function y equals 3. So we're looking at this function y equals 3 and the area below it. Now let's imagine that the x-axis being the center of a circle and that the function rotates around that center like this. So I've shown you step by step. So here's our function. I've made it angled a little bit just to make the illustration a little better. And we're going to rotate it this way. Here's what it looks like after a 90-degree rotation. We have a quarter of a cylinder here, a 180-degree rotation, it's a half cylinder, and then a full rotation, we get a full cylinder. Notice that the resulting solid is a cylinder, and the volume of a cylinder is pi r squared times h. In this example, the distance from the x-axis to the function is actually its radius. So that there, as I've written here, is the radius, and that the height is the integral from the boundaries. So this here, from A to B, that is actually the height. So r is the radius, and in this case y, the function y, is the radius, and that the height is the integral from A to B. Using this idea, we get pi r squared h being the volume of a cylinder. Substituting y for r, we get y squared, and substituting h as the integral, we actually get the volume of a solid rotated around the x-axis. Let's generalize this to the volume of any function rotated around the x-axis. Let's take a look. We have a function, looks a bit like a parabola. When we rotate this around the x-axis, we get this trumpet-looking shape. We have a cubic here. When we rotate this, we get this stretched out cylinder, I guess, stretched out sphere. Not sure exactly what to call it. And here we have the line. And when we rotate this around the x-axis, we actually get a cone. So the volume of a solid rotated around the x-axis is pi times the integral from A to B of the function y squared dx. And this same process can be generalized to volumes rotated around the y-axis, where instead here we had y is equal to some function of x. In this case, we have x equals some function of y. So here we have the area against the y-axis. And when we rotate this around the y-axis like this, we get this solid here. Notice how it's very similar, except we have x squared. So let's get to some examples. You can pause the video and give this a go yourself. So here we go. So for this, we establish first our volume formula. Volume equals pi times the integral from the two boundaries, x equals 1 and x equals 2, of the function y squared. So the function y is 3x minus 2, but we have to square the function y. And by evaluating this, we get the volume of this solid. So let's expand this. You can use the reverse chain rule, but I'm just keeping it nice and simple. Integrating this, we get pi times 3x cubed minus 6x squared plus 4x from 1 to 2. Substituting 2 into all the x's, we get pi, let's use squiggly brackets for this, times, substituting this into a calculator, we get 8 minus, and now substituting 1 into all of these, we get 1. And just evaluating this, 8 take away 1 is 7 times pi, and the exact volume is 7 pi unit cubed. And if we would like to get an approximation, 7 pi, that's about 21.99 units cubed. Hope you can see that's not too difficult. It's just following the formula. Let's keep going here. So we now want to make our formula. V equals pi times the integral from 1 to 3 of the function. Now here's where it gets a little tricky. We need y squared dx. But if we go back to our function, we have x squared plus y squared equals 9. Well, we can simply find y squared by moving 9 minus x squared like so. Okay, so substituting that in, we get pi times the integral from 1 to 3 of 9 minus x squared dx. Integrating this, we get 9x minus 1/3 x cubed from 1 to 3. Substituting 3, we get 9 times 3 is 27 minus 1/3 times 3 cubed is going to be 18 minus, substituting 1, we get 9 minus 1/3. It's going to be 26 on 3. And just evaluating that, 18 minus 26 on 3, we get 28 pi on 3 units cubed. I'm just going to leave it in exact form, but I hope you can see that all we are looking for here is y squared. Okay, let's move along where we do a few examples where we do this against the y-axis this time. You can pause the video and give this a go. So we're doing the exact same thing, but this time we're doing it against the y-axis. So let's start first by remembering and recalling that the volume is equal to pi from a to b of x squared dy this time. So the first thing I hope you can see for this is we need to make x the subject, or in this case x squared the subject. That's nice and simple. We get x squared equals y plus 1. And so now to calculate the volume is from -1 to 3 of x squared, which is already y plus 1 dy. Integrating this, we get half y squared plus y from -1 to 3 substituting 3. 3 squared is 9, so 9 on 2 plus 3, we get 15 on 2, minus half times -1 squared plus -1, we get negative half. Adding all this, we get minus minus, so it's plus a half. That's 16 on 2, which is 8 pi unit cubed. Okay, let's move along to the last example. Once again, we need some value of x squared. So we actually need to change the subject of this one here. To get this, we raise to the power of e, like this. So we get e to the power of y equals e to the power of ln x. These two cancel, leaving us with e to the power of y equals x. But we actually need x squared. So x squared is actually e to the power of 2y. And so that is the integral that we need to work with. So volume equals pi from 1 to 4 of e to the power of 2y dy. Integrating this, we get half e to the power of 2y. We get, substituting 4, we get half e to the power of 8 minus half e to the power of 2. I'm going to leave my answer like this in this exact form. Oh, and it's going to be unit cubed. And yeah, I hope that gave you an insight into how we find the volume of solids against the y-axis or even against the x-axis. So I hope that gave you an insight to volumes of solids using integration. Hope to see you in the next video, and best of luck.